take out this school, I should spend on where this stuff is coming from. Okay? And why they are going in this direction. So I want to spend part of the time now on introducing the topic. Okay? So the first thing that one should realize that when people started, let's say, Hagen Kastler, probably before that, started on this algebraic quantum theory. Okay? The idea was not to write down a Lagrangian, okay, or to make calculations on cross sections, but to get some structural initial motivation was to get some structural results which are encompassing any kind of quantum field theory you can imagine writing down, which are compatible with basic physical principles like causality, okay, especially causality and localization, and the notion of that. Causality actually encompasses also what is meant by locality in quantum field theory. So that was their focus. The beginning focus was this. And when trying to formulate it, they were led to this idea of algebraic quantum field theory and also addressing basic issues of observations. There are several issues regarding observations. One may have the impression that with all this junk about collapse of wave packet, that problem is solved. But one should really consider collapse of wave packet as a metaphysical statement. There's no basis whatsoever. And so far as I can tell, it is not the central attention that people are focused on now. Some people are focused on now. Okay? So these issues came up at that time already, and it is nowadays beginning to overturn many fundamental things that we are imagining about quantum, say, elementary particles. Okay? So I come to that. For example, it is now very clear that because of infrared effects in quantum electrodynamics and QCD, electron or any charged particle does not have a sharp mass. Okay? So you cannot describe it as a particle with a definite mass. You cannot describe it as a particle with a definite spin either. The spin or mass of these particles are spread out. Okay? But do they affect? But these are infrared effects. So most of the experiments won't notice. Okay? But it is a fact. These are the kind of statements that are nowadays indisputable coming from this analysis. So I want to go towards this kind of situation that is nowadays developing, okay, and see what are the consequences. Okay. So it is really structural. So what I'm going to talk about are structural results. The best analogy I can imagine is 1931 group theory paper by Eugene Wigner. He wrote down angular momentum selection rules, but the angular momentum selection rules were not targeting one particular experiment. It was completely, it didn't care about what the potential was in the nucleus, but it gave selection rules on what the transition probabilities are using Klebnikov coefficient. That's the kind of thing that is happening now. If you want to get more detailed information, you have to write something more dynamical, and development in that direction is only nowadays happening. The people who are doing this are getting confident enough to address such issues only recently. And nowadays, recently there are papers have come out, especially by the paper I know is by Friedenhagen and Kasia Reshner. Kasia Reshner was in Bengaluru giving a set of lectures 2-3 years ago. It is coming out, and nowadays they are able to do perturbation, at least formulate perturbation theory in gauge theories using Epstein-Glaser perturbation theory, which is causal. Okay? So incorporating causality and what is called the some of you may know the Batali-Minkowski cohomology. They are able to formulate it and carry out they are beginning to formulate it and carry out renormalization. So it is just beginning. This line of development is beginning, but the structural results which have come out, in my opinion, are very deep and all encompassing. That is, you can't. It's very difficult to imagine breaking them unless you break causality, or one breaks Lorentz invariance, as apparently happens in QED, okay, because of infrared effects. So QED and QCD actually are out of this. It appears that they are going to upturn our quantum understanding of quantum field theories as now known. Okay? Because if you lose both Lorentz areas and causal and I saw a remark in one of these papers that spin and stasis theorem is broken by because of the infrared effects in QED. How much? I don't know, but there's a remark. So these people don't make kind of remark casually. So there are many deep things going on, and I want to please communicate you these ideas and make you familiar with what is happening. I want to also emphasize, somebody was saying that it is too mathematical. In fact, Jelen was making that remark. The kind of mathematics that is involved is not the kind of mathematics you will find if you start studying, say, Laplace operator as an elliptic operator on a manifold with the boundary. It is very heavy. That kind of mathematics of elliptic operators and weak solutions, Somerville spaces, that's not the kind of thing that happens here. These are mathematics which is much more soft. And the main characteristics is that they are very robust. They don't change if you make small mistakes. The results won't change very much. But you need to know the concepts. Just like you need to know what is a group. When you start doing calculation, you need to know the concepts which are underlying this. What is the polynomial algebra? What is the problem? What is the problem that happens in digital space with this horizon? What kind of problem do you face? And why did Ed Whitson give a talk here in the work about the work that Chandrasekharan, he and Robert Longo did? Okay? So, why is that problem arising at all? Okay? So, if you look at what the Ed did, it's not difficult maths, but conceptually it is very rich. Okay? So, it may be wrong. Human beings are subject to errors, so that is not a problem. Okay? But what I want to emphasize is that the kind of thing that is happening has close analogies to what happened with Wigner. Okay? So let me now start again. I want to say, okay. So first, let me say a few words about algebra. Okay? So let me start with quantum mechanics. Okay. The way quantum mechanics is taught normally in textbooks or classes, what you are told is you are taught about wave functions and double slit experiment. This is the standard thing you find in textbooks. And the Hilbert space is brought in as a casual thing, as an afterthought. But you are never defined. It is never defined what exactly is meant by Hilbert space. Maybe they write a scalar product, but they don't talk about Cauchy sequences or completeness. And they certainly don't talk about manifolds with boundaries, which nowadays are dominating calculations in condensed matter physics, where they have surface integration. That analysis involves some quite subtle analysis of elliptic operators, which in fact involves hard mathematics, and it is done by these people like Kittel, and they get all Ed Whitson again. So, in my opinion, this kind of teaching of quantum mechanics is flawed, is extremely deficient. But that is how we are brought up, and somebody said they do it in MIT, but there is a problem of MIT, not us. So let them go on. Okay. So in this kind of calculation, the Hilbert space is brought in as an afterthought. You just follow Hilbert space, whatever it is. But the problem is that around 1940s, I would say. So, but this kind of thing is very strange because in classical mechanics, we see no trace of Hilbert space. So suddenly Hilbert space comes up in quantum mechanics, nothing in classical mechanics. What is happening? There's a total disjunction between two ways of looking at nature. And this cannot be. It cannot be that the nature is schizophrenic. It should be taken to a hospital. It cannot be like that. So there should be more unified explanation. And this was initiated in the 1940s, I believe, by the Russians, as usual. In this case, by Gelfand and Hammer, who addressing issues essentially motivated by quantum mechanics, they started looking at algebra. Okay. So I'll tell you how algebra come in this game. Okay. Uh, but they were conscious. I think they were thinking that uh, they were actually initiated the fact that both classical and quantum mechanics are simply different aspects of probability theories. The Hilbert case is a secondary concept. There is a corresponding notion in classical mechanics also, which is not very useful. Okay? But here it is essential. But it is an emerging concept. If you don't like Hilbert cases, you can trash it and purely work with a probability theory, not of a novel kind. Okay? So Gelfand and Namak seems to have realized it, but okay. So the complete elaboration of this line of thought, I would say, which was initiated by Gelfand and Namak, went to Siegel, and a lot of the physicists and mathematicians address this. And I would say that significant progress in understanding it was only happened recently by the work of Alain Coe. Okay? But even then, there are issues to be addressed. So let us say that that's a project. Okay? It is a project which tries to unify these two concepts. Okay? And yesterday I found an article review by Gleason. I think Sivashish would know about Gleason, who has actually given a set of lectures where he addresses exactly this. He also says similar things. I was surprised. And he also shows why classical and quantum theories are really two different aspects of certain probability theories. Okay? So let me go on to that. So let me first discuss a very general statement about physical theories. If you take any physical theory whatsoever, there is a quantum. Okay. It's okay, I can just move. So, if you take any physical theory whatsoever, definitely there are two aspects. The first aspect are you have a set of things you measure. Which I denote by script A, which is called this is a set of observables. This is what the experiment measures. These are the characteristics of the received thing, say in the ring, in the LSC ring. The received object is characterized by certain set of observables. Could be spin, angular momentum, charge density, whatever. Or maybe scattering, the amount that is scattered at some angle, anything whatever. Okay? The second is what the experiment observes. Okay? So what the experiment is makes a certain measurement, and the description of the experiment is given by give us symbol omega, and it is called a state. Okay? Neither element A nor omega have independent existence. Okay? You can't see them. Okay? What the experiment sees is the value of the evaluation of omega on A. This is what out the experiment outputs. So omega A is a number. So the outcome of the experiment is a certain number for omega A, which involves this coupling of the experiment omega with the observable A. So what is this A? Classical mechanics, neither in classical mechanics nor in quantum mechanics do we deal with points of space-time. Okay? This is mythology. We don't see points of space-time. What we, at least in the theoretical aspect, we don't. What we see are not points of space-time, but certain algebraic structures. Classical mechanics typically it is given by the Poisson. It is given by Poisson brackets. So they are given typically by functions on a phase space, okay? And which so. So there are functions on a phase space. So the algebra that we find in classical mechanics are functions which functions F it's at a point P of phase space, because it gives typically in classical mechanics real numbers. So they are functions. And the characteristic of the function is that there are two properties. First is that these functions can be multiplied because they are functions. If the multiplication property of the function comes naturally, I would say that if I have two such functions, f1 and f2, at a point qp of the phase space, it is the value of f1 at qp times f2 of qp, where these are two real numbers, so I know what it is. So this is already given to you. Now you may say that I am introducing points of phase space, but typically speaking, if you are very curious, I can represent this multiplication law in an abstract way. So I don't have to tell you that they are functions, but giving it by certain algebraic relations and generators and relations, and it will become it will become completely intrinsic without telling what the points are. So I will use the point of phase space as a convenience, but it is not necessary. If somebody insists, I can give you examples where I can make presentation of these algebras without telling where they are coming from. Okay. I will say this is my physical system characterized by this algebra. That's in mechanics. And in addition, these things have a quantum bracket.
Statement that the coordinates do not have a some of the coordinates of this space, or points of
yes. They will emerge. The great thing that Gelfa and Naimark did is that if you give me the algebra, just give me the algebra of these algebras have certain topologies, some continuous properties. Then I will show what they showed was that QP, the points, if you take this algebra and ask what there is a I'll come to your question right here. There are two properties of this algebra. One is that it is commutative. Okay. Because they are numbers, so it's a commutative algebra. Okay. And I will recover QP from there. Okay. I'll show you how. And they also have quantum brackets, which will eventually transform itself into commutatives. So how do I recover QP? What Gelfand and Naimark observed was that QP, or take this commutative algebra and you ask for this irreducible representation. The irreducible representations of a commutative algebra are given by points. Where, how does it give the irreducible representation? By the valuation of the function at that point. So, irreducible representations are representations where this is a commutative algebra. All irreducible representations are one-dimensional by standard research in algebraic theory, and so label them as P1, P2, P3. Let me not. Then what is P1, P2, P3? Take a function and evaluate the P1, get a complex number, real numbers R, okay, or it could be a complex number. So the points P1, P2, P3 are the irreducible representations of this commutative algebra. These points, what they prove, this is a remarkable thing, are exactly the points. They can be given a topology, given the topology we want. They can be, and the topology is exactly that of, let me say, rigorously a Hausdorff topological space, which is our normal space. Okay. What is lacking in their work was how to get the differential structure. Okay. I can, at that point, they did not do it, but they recovered. For example, if you take a circle, you take the algebra of functions on a circle. Okay. So, it's given by exponential in theta. So they are given labeled by n and m. So n, so multiplication is fm is f of n plus m. So you should think of it as exponentials. What are the spectrum? From this algebra, they will recover the circle, and each point of the circle gives an irreducible representation. And furthermore, the circle has a topology which we give. What I can tell you. Okay. And that topology is that of the circle. So they proved a duality. They proved that a Hausdorff topological space is dual to a commutative system algebra. Okay. What is lacking is to prove that Hausdorff topological spaces, what additional structure is needed. to get actually a manifold with a differentiable structure. Right? That was very difficult, and until Alain came along, and he showed that you need much more activity using things like Dirac operators, purely algebraically, and he recovered the entire differential geometry that nowadays taught with Riemann geometry, Riemannian coordinates. You don't need it. Alain Cohn will tell you how to do the entire calculation purely algebraically, and it is much more flexible. Okay? You can do more things than you can do with manifolds. So the problem appears to be solved, but there are issues which are come. Okay? So is it by duality? You take these algebra functions and look at these irreducible representations. The irreducible representations are the points of your manifold. That's how it comes. So by duality. So the points of the manifold are emergent from the algebraic structure of classical mechanics. Now, there are issues I will come to. Okay. So I should tell you. Huh? How do you mean? No, I don't. That is not what we know. I don't know about fundamental business. What I know is that what we do in classical mechanics are to deal with functions. That is what I know. Okay? We don't deal with points. It is a complete misnomer to think that we deal with points either in classical mechanics or in quantum mechanics. Okay? I tell you, the situation in quantum mechanics is much worse. Okay? To deal with points, but classical mechanics we don't. That's not what we do. Okay? You can't take Poisson brackets of points. Please tell me how you will take Poisson brackets of points. You can't do it. Okay? So that's not what we do. Okay? What we are doing is right a certain algebraic structure is the Poisson algebra, which is a commutative algebra with Poisson brackets. Okay? Now you can ask immediately, what does it mean? You mean algebra? Where is it coming from? Then get for an IMAR and Siegel will tell you that it's coming from a certain topological space, which is the kind of thing we are dealing with experimentally. Our brain is receiving information on the table, for example, from this data. There are issues here which are open, which will come to later. Okay? We will come to in the past. But I cannot tell in this calculation what is in the classical physics, what is a state on this algebra, and the state here is, you can again define the state abstractly, but again Gleason gives a reference to a theorem due to Ries and Markov that any state on such an algebra can be written as a probability distribution. So we can write without loss of content, you can write it as the function f evaluated at some point p. So I'm pretending that these functions are actually functions on a manifold will come later, not to confuse people. Let me write like this: multiplied by some density function omega integrated. Okay, so these are some Leibniz integrals, and there is a sigma algebra. If somebody is interested in probability theory, so you write like this, and this is omega is a probability, so it is normalized to is positive. Omega x star f is non-negative, and omega at 1 is 1. Okay. So positive function is non-negative, and on total probability is 1. Okay. This is a characteristic of any probability, and this is what we do in classical mechanics. So as I said here, there is no need to write omega by Bessel integral. Okay. It's a convenience for us to perceive what we are talking about, where it came from. But if you don't like it, you can put it away and look in some the work of Ries or Markov, and you will find these results from what I understand from Gleason. So here I actually normally we deal with real functions, but it is better to deal with complex. You can easily complexify. Take this algebra and complexify its coefficients, so you can easily extend it to the complex coefficient functions to complex numbers. So you get a complex algebra, and what is the real subspace? Well, on this complex algebra, I can define a star operation. Say this use in a sneaky way upstairs. When I said that omega is positive, I was using this some star operation. So you may ask what is meant by star on a real function. What I mean is I complexify it and I define on the complex functions a star operation, which will be the complex conjugate. So the star operation on the algebra will be the standard complex conjugate part. So, and its real section, there is all functions which are not changed by star will be the real section of this algebra. Okay. No, you may also there's something more even equally much more important somehow. But just take functions. We need to give we need to have some measure of its magnitude. How big is this function? How small is it? Some topology is necessary. Cannot say some table, some private person, experimentalist says this is my error.
But whatever you are saying, this full system like harmonic oscillator.
Yes. That is, yes, we can do.
That will be more useful.
So you can ask me a question. I have not prepared notes on harmonic oscillators because there will be no difference. This is true for any quantum mechanical system, in a classical mechanical system, given by a phase space. Whatever I have said here is true. Okay. Now, if I say harmonic oscillator, I don't have Hamiltonians. This is not, they said at the beginning, it is not addressing a particular physical system. Like Wigner did not address a particular nucleus, but it will apply to any classical mechanical system you do. Okay. Anything. Your harmonic oscillator is given by Q and P. These equations will apply. Okay. You do if you hydrogen atom, it will apply. And so, where functions on a phase space. Huh? Right. Any smooth, any continuous function is fine.
How do you extract the dynamic? Let's say the periodicity of the harmonic oscillator.
And for that, you need an evolution operator. So that will involve dynamics. And as of now, I have not put it dynamics. You can put it as an extra thing, but I have not done it. Okay. You can put or you can put something else. Okay. You can put some recording system. No, this is too difficult.
Basically, one can also, in quantum field, can do space-based
physics. I'll come to that quantum mechanics. Good point. So first, I have to tell something equally important. I need to define a norm. Without a norm, norm and topology are ways of measuring how big the observable is or how small the observable is, how near they are each other. We want to have a formal statement, not somebody experimentalist writing some table and saying, maybe adequate for some purposes, not for our purposes. So what is the norm I will put? The norm that Gelfand-Neumann found, and I think this is very clever, was to take the supremum norm. So the norm of a function f is the supremum of all the states of omega f. Okay? Evaluate omega on a function is a real number, and you take a supremum, and that is the norm. For example, for a function defined on a phase space, it will be the maximum value of the modulus of the function on the phase space. This is equivalent to that definition. So take the function on the phase space, take its maximum in modulus, define it to be the norm. It's very natural, and you see that it generalizes n by n matrices, generalizes to boundary operators on a Hilbert space, all kinds of things. What is the most important property of this norm is that it fulfills so-called C star property. What is the C star property? The norm of f star f. F star is the complexified function f, and f star f norm is modulus of f squared. This is called the C star property, and this is the central result that one has to do. Okay. So now I have a commutative algebra which is normed by this equation and states on this algebra. This whole structure is what is called a C star algebra. This whole structure is what is called a C star algebra. The C star algebra is not the commutative part, the norm part, and the algebra or say complex numbers continue with the norm given by fulfilling this equation is what is called a C-star algebra. This is what, so far as we know, underlies both classical mechanics and quantum field theory. So the Poisson structure has to be compatible with the C-star property, and so far as I know it is. Okay. So the finite transformation by Poisson brackets to exponentiate and they maintain their I don't know whether they are unitary. They are called what they are called, but they maintain. So you make a finite translation in the QB space, exponential of the Lie derivative with regard to some function on the base space. Acting on this, you will find that it maintains this property. The Poisson structure is defined by the commutator. Okay, right? Right? No, that is a different. No, it's a different thing that comes. Okay. So one has to check that relation is compatible with the C-star structure, and one can check it easily actually. But the Poisson structure also has Jacobian identity of one, which I did not write now. One can check that relationship is compatible with the C-star structure that I have written down. In the sense that if I is like in Lie algebra. In the Lie algebra, so any element of the Lie algebra acts on anything else by commutator. Okay? But is compatible with the group structure because I can exponentiate this. Lie algebra act on an element of for the algebra, and what I get maintains the Cartesian form. So it is maintained, and likewise here also it is maintained. That's the easy part, I would say. Okay? So I did not write it down, but we can discuss it. Yeah. Here I cannot answer you very clearly because the Gelfand, Naimark, Siegel pulled it out because they needed this property to get the spectrum to be a Hausdorff topology. So what is a Hausdorff topological space? Some of you may not know. It simply means that if you take any 2 points on this space, there are open sets which covering both, which are not intersecting, which is we normally think. Okay? But there are topological spaces where this is not true. Okay? For example, if you are familiar with Raphael Sorkin's work, he gets partially ordered sets from his activity on causality. Okay? They are not Hausdorff, they are what they call T0. Okay? They are completely, you can only separate one point, not from the other. Okay? So you cannot find open sets around both which don't intersect. That doesn't exist. So here they wanted Hausdorff topological space. I think they put it. I think. Okay? So they can prove a duality. Here they can prove a duality. There you cannot prove such dualities. So I think that was the motivation. We need a stronger physical motivation. I don't know it, but Haag in his book again raises this issue. There are long discussions about this, and he says that he and Kafka settled on the sister and others. I think there were others involved at that time also. They settled on this sister property and the polynomial algebra property because of its closeness to certain. So maybe mathematically this is said, also physically they were motivated, and Haag discusses what the motivations were. Can I change it? I don't know. Maybe you can. I don't know. So this I think is not a clear thing in my head. Hausdorff property is from the duality. So there's a duality. Right? So
I thought this property was also sister property was also
continuity of
the algebra itself is a topological space.
That is in this norm, yeah.
That is of the multiplication operation on the.
Hmm.
So the continuity of that operation requires this property. That operation has to be continuous.
Yeah, I think
That is fine.
you may be right. There is some remark of this kind in Gleason's lectures. Okay? And I don't. There is some property. I think it's good to read this, at least. There is some property because a separability of the sister algebras, okay? Which is related to your question. I don't want to tell what I. So, if this norm put there, it is possible to find a countable set of elements of F of the algebra which are dense in the full algebra. So you can separate the points of this algebra. They are not sticking together, and you cannot put anything in between. So he states it as an important property. We assume it normally. So it may be related to that, but again, I'm not sure. I don't know. I have not seen your discussion.
This condition is what defines system.
This condition is what defines system. No.
So anyway, this is a real function ordinary.
Wave function is not an algebra.
Real function.
Real functions with, I mean, I will tell you what is many models. If you take the supremum norm, is
So it's a system.
if you take the supremum norm, but there are other norms that can go. For example, LP norm. You can say norm of a function is what f to the power of p integrated over the space and what p through. It's a perfectly good norm. Okay. It is the triangle inequality and so on. But that is not this stuff. LP norm regular. L infinity, there is this stuff called L infinity and so on. So,
So in the structure, in the Poisson structure have degeneration.
the Poisson structure has in this calculation. I have not used the Poisson structure. The Poisson structure has degeneracies. Then what will happen is that you have to quotient them out. You get you see this quotienting necessity, when I go into what is called how do I get a Hilbert space? I am not talking about it. I'll come to that. There is business of null states, kind of thing you're talking about. Two, okay? Then you have to quotient them out. Okay? In the algebraic structure, you have such null states, things commuting with everything. They generate a two-sided ideal. You know what I mean? So they form something in the analog of invariance of algebra. So you can quotient them out. And you again get the new algebra, but that won't be the original one. So we'll come to that. It happens in many cases, but it's not sufficient for this discussion. So, so, so what I have got in the classical mechanics is a commutative Caesar agenda and omega is a state term. This is characteristic of any measurement theory in classical mechanics, and it all turns out to be of any measurement theory in quantum mechanics also. Without this, you have no physics at all. So you have to put something like this at some stage in any calculation. Now, as you say, how does one deduce a manifold from this data? So here I give the quote. Okay. The key question was already addressed in 1943 by Jeffernheimer, and then Siegel. Siegel revived this data in the, I think, late 40s. Okay. And it was only solved, big progress was made only by Alain Cohen recently. And if you read his book, it's just a very difficult problem. And the book by Alain Cohen and Mathilde Marconi, which has come out not so long ago, discusses it in considerable detail, and it is what goes into the formulation of the standard model a la Alain Cohen. Some of you may be familiar with Alain Cohen, Ali Shamsuddini, and so forth. who have computed Higgs mass using their model, and it's all based on this work of array.
Just a small clarification. Having a manifold structure with the algebra of options.
So they start with again for yeah. So you can ask the following question. I'm not sure. So if you're given C-star algebra as your preliminary data with appropriate properties, then your interest may not be in computing the manifold. Your interest may be in computing some probabilities, some expectation values of zeros. So then you don't care about the manifold, or you may. Depends upon you. For example, such a structure involves also finite dimensional matrix models. There are also similar the matrices, n by n matrices. You take the n by n matrices, they form an algebra. You can multiply them. They have commutator which replaces Poisson brackets. What is the norm? You define the largest eigenvalue. There's mod m. Take m star m, which is self-adjoint. Take his maximum eigenvalue. Take his square root. Define the norm. That is a C-star algebra for matrices. Now, from there, I may not want to go ahead and find the manifold. You can also do it, but it may not be of interest because you may be doing something on quantum information, collapse, measurement of spin entanglement, things of this kind. You may not be interested in the manifold. The manifold may be something very boring. So it depends on the issue. Alain was interested in seeing how to replace all of differential geometry by algebraic structure. That was the central problem for something like 40 years more. And it seems to have been, I wouldn't know if it's solved, but great progress has been made. Huh? Can you come? My hearing is not good.
Differential geometry of what?
All differential geometry.
Phase space or
Take R4. You don't need phase space. So in this calculation, you don't need take R4. You don't need it. So in Alain calculation, I think what you need is some C-star algebra given to you along with what is called Dirac operator is abstractly defined. From there, he is able to, and there are some additional things like which I don't know, the Tomita Takesaki theory and all that. And then he says, and I think it's true, that he can get all the results of standard differential geometry, all of it, and more. You can do many more things with this than you can do with that. And he proves long-standing conjectures in Riemannian geometry by these techniques in this various publications. So because algebraic properties, algebraic approaches are much more powerful. For example, if you take two quantum keys at the same point, you can't multiply them. People do multiply in regular, but you can't really multiply them. They are distributed. You get square root of the delta function. Then you are bothered that it has to be renormalized. But one did something wrong at the beginning. But here you can handle it. Okay? So it is it's a more flexible. It appears to be a much more flexible situation. So let me give you an example. Take quantum Hall effect. Here is a non-static one problem I can imagine. Take quantum Hall effect on a disk. Okay. Now the boundary of the disk normally is taken as a circle, and that is where you see the Hall current. Okay, I won't take a boundary of the disk to be a circle, but I take it to be a Julia set. Okay. Completely rumbled. Okay. So I cannot define any differentiation on the boundary. How do I define the Hall current? How do I describe the Hall effect? Okay. If you do what is done in textbooks, you will get into a mess right away. But in algebraic approach, there is a way of handling this algebraically, which describes this highly crumbled structure by certain differential operators. This is related to this Virasoro algebra, and the formulation is actually given in his book. One of my ambitions for a long time is to take it up and actually apply it to an experimental situation, because you can prepare the samples experimentally with a disk with all kinds of edge deformation, but various distractions and time constraints I have not done it, but it is a fact. The maths refers are in this book on what's it called? In this book on non-commutative geometry, he has given this maths result in passing. So, okay.
So, yeah. So, if you, is there any certainty when you go from finite dimensions to infinite dimensions?
Finite dimensions become clear. No.
There are no.
The formulation is the same, but it becomes more trivial. Many things that happen in infinite dimension do not happen in finite dimension. And in fact, one of the points of discussion will be, you will see that in infinite dimensions, there is absolutely big translation invariance in the Hamiltonian bounded below. There is no localized thing whatsoever. So the bond localization simply does not work. It's not true. But we do it in non-relativistic mechanics. So, but in finite dimension, there is no such problem there is. So there is a big difference between the two cases, and in fact, the Wittgen's reviews discusses why this happens. He actually takes a finite dimensional system and shows that when you take a large n limit, depending on how you take the limit, you end up with totally different structure. This is known for a long time, that is related to some results of Araki and Woods, but he shows it pedagogically in one of the reviews at Princeton when he gave a set of lectures on this matter. It's available to them. So there is a big difference between finite. So I find it a bit disturbing that people doing quantum information always do finite dimensions. But that is trivial. Okay. Who wants to do finite? I want to do infinite dimensions. Okay? Or I don't know that nature is infinite dimensional, but I know for sure it is not finite dimensional. It is something in between, maybe. But what is it? I don't know. Raphael Sorkin thinks that it is a partially ordered set. He may be right. Because many things like spin statistics, causality, nothing can be defined in finite dimensions. Please divide for me. What is causality in finite dimensions? Already Faraday told me that to describe causality, you need a field. So that's how the fields came into the picture, right? Law, interactions at the distance, he started worrying about what's it called, some name he gave for some intervening field, which went to Maxwell and so on. Already at that time, people understood that to formulate causality, you need a field, but that has infinite number of dimensions. A priori. Do I need it? I don't know. There is no such thing as a lattice. What is a lattice? Please tell me. I don't know what it is. I don't know that I'm starting algebraically, and if you give me things which we colloquially say, I cannot answer it. I don't know. You should, I think, discussing fundamental problems, you should totally avoid classical language, if possible. To the extent, only, what's it, to our advantage and insight, we can use it. Otherwise, we should avoid it if you want to make basic statements. Okay? So I don't know what the lattice. I have many objections to lattice. It may be right. It may be that the lattice theory is the right one and quantum field theory is wrong. It's possible. Okay? I have no problem with that. But for sure, finite dimensional matrix models are not a good reflection of reality. That I can be very confident because this has many basic issues, like spin statistics. Spin statistics is absolutely fundamental. We know that. It has very macroscopic effects. For example, we know that most of molecules and atoms, there's a lot of empty space between them, huge amount of empty space. Issue arises, why can't I then cross one finger right across the other? Like Indian Swamijis do in Himalayas. Just cross right there. Why not? They are empty. Why can't I do it? That's only because of spin statistics. So there are macroscopic effects from spin statistics. You can't ignore them. I don't know of any way of deriving it from matrix models. Are they relevant for the kind of calculation I do? I don't know. So there, our judgment is involved. Is it important, not important? I thought that depends on the particular issues one is solving. Okay. Now, so I will assume. So this is the framework of classical mechanics, classical physics. What issue? So one thing I should say in classical physics is something very important, that if F is the element of this algebra, then I can construct this exponential IF. F is suppose real, I can construct exponential IF. It's also a good function. I can evaluate it because if I know what F is, I know what is exponential IF, and it looks like unitary. If I take U star, it is U inverse. So U is a unitary operator. So I can ask whether the conjugate elements of the algebra do I change it. In the commutative case, I don't change it. So because A is commutative, it doesn't change. So this is a property which should not be maintained in quantum mechanics, and this will cause a lot of trouble in understanding what we are doing. But if I do this, the algebraic structures will not be changed. I mean, in this case, nothing changes at all. So, what are the if you give me a commutative algebra like this, or algebra of functions, I can ask, how can it permute the elements without changing the algebra? To my knowledge, the only thing you can do are the underlying topological space, which you get, for example, from Gelfand-Hamer construction. You can make diffeomorphisms or homeomorphisms and then lift it to the functions. This will not change the algebraic structure. So, if you measure when you get the manifold structure from the algebra, you will only get it up to diffuse, up to the diffeomorphism class of that algebra. That's only ambiguity in the algebraic structure that we get recurred in the end. But this will become a very important issue when we go into quantum mechanics. So I assume that for some reason or other, classical mechanics, you give me the commutative algebra, the measurement problem is solved. What do I mean by that? By making measurements on the classical observables, I can recover what is the space-time on which I am doing work. What is the dimension of the space-time I am working with? What other questions I can ask? I assume that. Is it true? I don't know. There are already problems here. For example, I give you an algebra. For example, algebra on a phase space. Algebra and phase space are all functions of Q and P. Which commutative algebra do I take? I'll get, for example, for a harmonic oscillator, I have to take the algebra functions which are only functions of Q, independent of P. How do I know which are the functions of Q alone? The whole thing is not commutative. Which commutative algebra do I take? There is a problem. I don't know how this is solved. So I assume, as most people assume, that classical physics has no measurement problem. I don't think this is correct. But on the other hand, I have no clue on how to approach this issue. How do I recover information about people like Jalan or somebody in my head? I suppose I am only measuring some algebraic structures coming from him. How do I recover the fact that he has a nose and he's sitting there? How do I know it? I don't know how this happens. So I don't think that classical measurement problem is solved. So I will assume that somehow or other it is solved.
Are you saying that outcome set of measurements can determine the state?
No. How do I measure the set of measurements? This will determine the class of states. But I have to determine which observables I look. If I say phase space, and I say commutative algebra give me phase space, but I want to know what is the harmonic oscillator. How do I know I am doing harmonic oscillator on a line? I have to take functions on Q, which are independent of P. How do I know? Because I am only given the algebra. The functions on P and functions on Q, they are all isomorphic. There is no change. Both are commutative. P goes from minus infinity to plus infinity. Q goes. So how do I pick the algebra I want? That is the problem. Okay? At least I don't know how to solve it. So there are things here which have to be resolved. So let me go into quantum physics. So yes,
From the measurements, can we say if the particle in the box or harmonic of it?
no. All that I know is some observe. I don't know whether you can or not. All that I have a table of phase active algebras. You take the table, then depends on you put things in a box, things are horrible, becomes horrible. So don't just take nice box. Box has a boundary, so you take R3. You take phase space. Then I am giving you algebra functions on R 6 dimensional space. Namely positions and momentum. It's commutative anyway. How do I know that? How do I get the dimension? What do I get from that? I get a table. When I get a fuse table. From there, how do I know which manifold I am working with? I don't know. I can tell you that I am working on R6. That I can tell. But it's my space-time three-dimensional, I cannot tell. Spatial size three-dimensional, I cannot tell. There are, for example, take particular circle. Phase space is cylinder. Take all functions of the cylinder. From there, can I tell that I am working on the space-time is the same, spatial size is the circle? No. I get the whole cylinder. So I need to have some device to pick the right algebraic structure to infer the nature of the spatial size I am looking at. And I don't know how it is done. Somehow we are doing this in our brains, and I don't know how to do it. There's some processing that's happening in our interaction with nature, which I don't know.
Yeah. Supposing I have a system, you are saying that phase space is not relevant. Functions, algebra functions can be. I'm confused. Without space, how do I define?
So that's what I said. The algebras can be defined abstractly. For example, so right there, I'm told that the people who are looking at me online can't see me. Okay? So I'll give you the algebra which you can infer for a circle. I tell you the algebra without telling anything about the circle. The algebra is labeled by integers, m, and then this is the basis, fm. Then I say fm times fn is f of m plus f. Okay. And then I take all complex linear combinations, and that happens to be, we can easily define a norm, and it is a sixth algebra. Okay. What from here can I infer that there is a circle? In this case, yes, because fm is what does the fm stand for? It stands for the function exponential I and theta. So theta is the coordinate of the circle, and code shows how to recover the circle, or get one I'm sure how to recover the circle from that case. But in more complicated cases, what do they do? Maybe in Möbius strip, I give you functions, space. I don't know how I know that I am working on a Möbius strip. I don't know. I am sure that people have thought about it. But I have not seen the literature. I think Gleason's lectures have remarks which suggest that he has thought about it. But I did not see this kind of difference. So I will just say a few words and I will stop.
I look at the observed values, observed values of some vision, one vision. Can I not figure out from there what is the system I am dealing?
See, the point is the problem. I don't know. Suppose I am a classical baby. I'm brought up from the very beginning by good parents were only giving me algebras and functions and states. I am not telling anything about manipulation. The baby is brought up on a diet of algebra, cognitive algebra since state. How does it know that there is a word?
Experiment basically we observe values and corresponding probabilities. From there, can I not figure out what the system I'm reaching?
Only by, if you go from the theory to experiments, only by using the root of, there will be other roots, but
Take one.
this root only by applying delta and I'm here. But in the algebra I am picking has many more elements than what represents the spatial manifold, then I get some completely different results. Okay. So the particle dating will be completely confused. It will not know a donut from a hole in the ground. If it is just brought about as computing algebra and state works. Similar problem occurs more severely in quantum mechanics. This is what is available now. And I like a quote from Hegel that the owl of Minerva flies at night. So only as time passes is the what is potentially available is revealed. As of now, this is the situation. And just assuming recklessly that classical mechanics has no measurement problem. I don't think this guy, but it is more less severe than what happens in quantum mechanics. Because quantum mechanics there is the additional problem of the unitary transformations, changing the elements of the algebra. So it really gets confused. I'll come to that maybe next, because it's time I come to the next time. Okay, go on.
Question. Collection of measured numbers for the same observables which you have as a one parameter family of these things will tell you what the system is. If you have that, because that also has an inbuilt evolution as a one parameter family, which we will identify when say a harmonic oscillator or
but suppose I don't know what is harmonic oscillator.
no, but we will call it harmonic oscillator if it has this kind of. That's all that is.
Okay, that is a possibility. I can declare that a certain class of numbers is described in language by this thing. I can say that. That I can. But that is no problem. So you are just, you can also call them alpha, beta, gamma.
As a function of parameter t, to know the alpha 1, alpha 2, alpha 3, something, and for a collection of observables. If I have that, I can identify that as evolution from a particular state, whatever, or state, over a field of one parameter. I will identify that as parameter.
So I have no problem in naming a collection, a table with a name. This name can be harmonic oscillator, you can call it Henderson, I don't care, or you can put some Albanian name because what does it know where Albanian language name was?
Collectively something.
That's fine, no problem. Whether that has anything to do with what my brain recognizes as going to other people.
What you and I agree, you always agree on every time.
That's fine. I have no problem. That may be adequate. Your answer may show the way to a solution. So, anyway, I will next time I will say what the problem is in quantum theory. And then I will want to tell you about the, how probability for genus omega, the state on an algebra, I can recover a Hilbert space, and what are the how do you recover it explicitly, and also discuss things like entropy. I want to dispel the illusion that entropy is uniform. I'll show you that there are explicit examples which are new for a long time. That entropy is, you might have many states giving exactly the same, there's no uniqueness of a state on an algebra. I didn't say anything about the mapping from states on algebra being checked. So I didn't say anything about two states not giving the same set of numbers. That is not true. There is a whole class of cases, several examples, it is the same numbers, but their entropies are totally different. So which do I take? And then there are, you can prove results that you don't measuring one day, one stage for a minute. Look at a entropy will increase. Okay. Except S theorem of Boltzmann, I doubt maybe because that comes from some properties of convex function or concave function. And whether it has anything to do with Boltzmann wrote an S theorem, I don't know. But I will show it to you this and show some evidence. Then I will go on to do quantitative calculation. I will not go deeply into quantum analysis unless there are people who want to discuss something. Then I'm not an expert, but I know something. So I think I stop here. Where I can
The state, the omega is different. So we will understand the difference. The observer is the and then you define, you say there are two kinds of objects. One is A,
What is omega?
another is omega. So what is the differentiation?
Omega is a state, it's like a density meter.
Okay.
Have you a perception?
No, I'm the first one, but I don't know.
Okay. Omega is a state, that is the state by definition gives you numbers when you evaluate it on the algebra. Algebra are the observable or the received system. For example, in LSC, there are strongly interacting particles going around the thing. And they are going around, you don't know anything about it. Omega is the experimental detector, which gives a number. So omega, the detector by itself doesn't give anything. When the detector is applied to the ring, I get the number. Omega of A is the application of omega to the ring. Otherwise, the omega is just some normal. Two words, they don't talk to each other. But experimentally, we put them together, then we get number.
So usually like we say that observer is momentum or energy, like momentum and then these are like observables. So if you are A, that kind of observable.
Momentum and energy as operators
Yeah.
are observable of a quantum mechanical system. But by themselves, you can't, you need expectation value. Because the number, you need expectation value. That is given by omega. Okay. I will show you that omega can be written, omega of A, omega of X can be written as an expectation. Okay. I'll show you.
I have read the book. One thing, in the mathematically important say, but equally the book even or it doesn't equal a new study as one is doing it.
So it is like group theory. Group theory doesn't give a new theory, but it gives
Can you send me a here?
I think
I think the review
I'll send it.
you said group theory is not the-
Group theory doesn't give you a theory, but it tells you what will happen in any theory we produce. For example, giving a selection with an animal. It says it will happen anytime there's an atomic transition with a speculative infinity potential. Doesn't care what. That is here as of now. This doesn't tell what quantum field may be. It applies to all quantum fields. In fact, all of quantum physics.
So, sir, if I am doing quantum physics, let's say in university, like, will I be doing something wrong?
You violate this.
Like, what I learned from Griffith, what I learned from Griffith, university is
Basically,
yeah.
you will not be necessarily doing wrong. I have to look at what you're doing.
Griffith's quantum mechanics, basic principles of quantum mechanics. Hilbert space is there,
But why? No, you will not go wrong. But it will be mystified because where did the Hilbert space come from?
Yeah.
It is not there in classical. So this approach is clarifiable in the quantum mechanics. But there are also other issues that are related to quantum mechanics, which will be taken up by this approach. For example, if you have a manifold with the boundary, you try to do quantum mechanics, issue immediately comes up. What do I do with the boundary? So in Laplacian, it's not defined. pure boundary as it stands. You need boundary condition. What do I write? But there are actually infinite number of boundary conditions you can put to make the Laplace in simultaneous, and they give different physics, and they are coming up in surface excitation in kind of matter physics. So which to choose? Standard quantum mechanics won't be linear.
So it will not be independent matter.
In that situation, you will not be able to proceed, and you will be forced to read Kitaev, Hedwig's papers, something on elliptic operators and so on. You will spend several months learning something else. So this kind of approach actually acclimatizes you to the question. I won't be talking about it because of time. So I have written, what is separate joint operator? What is the domain of an operator? I don't want to give those things. Can be done, they're very useful, but I don't want to read it. So there's a few lectures, so I didn't know. But if there is no statement, you can